Hello and namaste everyone. Welcome to this lecture 33 of this NPTEL course on stochastic approximation. So recall that during this week and the next week we are going to be discussing two variants of the standard stochastic approximation algorithm that we have discussed so far. One is that of 2-time scale stochastic approximation and the other is that of stochastic recursive inclusions, right? And instead of directly describing what they are and so on and so forth, my goal in the previous class as well as this class is to set a stage for why we may even want to consider such variants, right? So if you recall, in the previous class we looked at what we called as the stochastic approximation variant of the Kaczmark's algorithm for solving an undetermined system of equations, right? And at the end of the previous class I asked what if some of the measurements of this random variable y, right, were adversarial in nature, then what would one do, right? In this class we will try to answer that question and go into a position where the utility of 2-time scale stochastic approximation algorithms becomes natural. With that in place, let's begin our formal discussion. Right. So let us do a quick recap. In the previous class we considered this linear model y equals ax, where x and y are random vectors and a is an a priori known matrix, right? And we asked, given access to samples of y, how can we go about estimating expected value of x? Towards that we proposed what we referred to as the stochastic approximation variant of the Kaczmark's algorithm, right? And its update rule was as follows: at time step n, given xn, right, xn plus 1 was computed using the following formula. So alpha n is your step size, calligraphic yn plus 1 is independent sample of the in plus 1th coordinate of this vector y, right, and ai transpose I is the ith row of a, and ain plus 1 transpose similarly is the in plus 1th row of a, right, and this is the transpose of that vector, right, and this in plus 1 we presume that it is sampled uniformly from the set 1 to capital N, where n denotes the number of columns of A. In other words, we had presumed that this matrix A had dimension n cross D, right, and we said that such an update rule, right, one can show first of all converges to x star, which is the solution of this problem: minimize x minus x0 the whole square such that ax equals expected value of y, right. So the niceness about this algorithm is that this is a noisy algorithm, but nevertheless it will converge to the solution of this problem which is deterministic in nature, right. So that was nice about this algorithm. However, this approach is useful when these measurements of y, that is these calligraphic yn plus 1, are generated by honest sensors or appropriately working sensors, but often in practice some of these measurements come from faulty sensors, or they are generated by adversaries, right. So in that case one can ask, can we continue using such an algorithm, right? In particular we will in this class and also the next couple of classes we will focus our attention when an unknown subset of n coordinates of y, right, are adversarially controlled, okay. That is, whenever in belongs to this set of adversarial indices, right. So a here is presumed to be a subset of 1, 2 capital N, right. So we will presume that this is the index set of adversaries. So whenever in belongs to calligraphic A, right, this calligraphic yn plus 1, instead of following the inth coordinate of y's distribution, okay, we can presume that yn plus 1 is generated adversarially, right, and it may be generated to derail your algorithm, right. The purpose of this algorithm is to estimate expected value of x, and these measurements could be generated by adversary to derail your learning algorithm, right. So one can ask, okay, how do we make our algorithm robust to such adversarial measurements, right. So to design online stochastic approximation algorithms for such scenario, what we will do now is to look at a simpler problem, take insights from it, and then use those insights to design this desired stochastic approximation algorithm, right. So what is this simpler problem? Okay, suppose the problem is as follows, that there is some vector x star, right, and we would like to recover it. However, we do not have access to x star, instead we have some linear measurement of x star which is a x star, right. So if this E was not there, right, the question is basically, given B, can we recover x star, right, using B. Okay, so this is like solving a linear system of equations, and there are several algorithms for solving such a linear system of equations, right. Now suppose instead of V being given a x star, let us say we are given a x star plus E, right, and we will presume that this E has the property that its L0 norm is at most q for some known q. So L0 norm is basically the number of non-zero coordinates, right. So L0 norm being at most q implies that at most q many coordinates of E are non-zero, right. So in that sense this problem can be interpreted as follows. Instead of being given a x star, what you do is you take a x star and the adversary corrupts at most q many coordinates of a x star to construct this B, and this B is revealed to us, right. And now the goal is, can I recover back x star from this adversarially corrupted measurement, right. So you can imagine this vector E to be an adversarial measurement with at most non-zero coordinates, right, and given this vector B, right, the question is, can we recover x star. Of course, if you know which coordinates of a x star have been corrupted, then in some sense it is an easier problem, because whatever are the corrupted coordinates, you throw those coordinates away, right, and from the remaining you try to recover x star, right. So that is a relatively simpler problem. Here we are considering the situation where we do not know which coordinates of E are corrupted. All we know is that at most q many coordinates are corrupted. So given just this information, the question that we are interested in answering is whether we can recover x star, right. So it is natural to see that in order to recover x star, we have to ensure that the information in a x star is redundant, right. Redundant means that the same information in some sense appears multiple times, so that even if a few coordinates of a x star are corrupted, because of this redundancy in information, from the remaining measurements we can recover back x star, right. So the key idea that we often exploit to handle the adversarial scenario is this concept of redundancy, right. So recall that when we were discussing solving this y expected value of x from this measurement y equals x in the previous class, we had presumed that A is a wide matrix, meaning the number of columns is larger than the number of rows. However, in this scenario, that is the scenario where some of the coordinates can be adversarially corrupted, right, we want redundancy, and in order to ensure this redundancy, what we will do is we will henceforth presume that A is a tall matrix, meaning the number of rows is larger than the number of columns, which means that if so in our case this capital N is the dimension of the number of rows. So your A is of dimension n cross d, right, and what we are presuming is that n is larger than d. So this means that for a d-dimensional vector we are providing additional information about x star in the form of a x star, and from this redundant information that is present in a x star, the hope is that even if a small subset of this coordinates of a x star are corrupted, right, we may still be able to recover x star back, right. So towards this there is a very fascinating paper which I have put up over here, that came in the year 2011, right, which discusses a sufficient condition on A that enables recovery of x star. More specifically, if you look at proposition 6 of this paper, right, the one that I showed you before, okay, it says that suppose your matrix A satisfies some condition like this, right, then if you solve the L1 minimization problem Ax minus b, right, and if you find the x star or the solution to this problem, then the solution to this problem will indeed be x star, right. So let us digest this one more time. This result, okay, provides a sufficient condition so that from an adversarially corrupted measurement of x star, which is a x star plus v, if you solve this L1 minimization problem, notice that there is 1 here instead of 2. So if you solve this L1 minimization problem, right, then the solution to this L1 minimization problem will indeed be x star, right. So even if there are adversaries and the number of adversaries is at most q, and this sufficient condition is satisfied, then we can recover x star. So let us try to digest what this sufficient condition is. The sufficient condition requires that this quantity be less than this quantity. So what is there on the left hand side? You require that the absolute value of AI transpose X, right, where recall AI transpose is the ith row of A. So absolute value of AI transpose X for every I in this set K, this should be less than a similar sum where I goes over K complement. Now what is K? K is any subset of the index set 1 to n such that cardinality of K is Q. So in other words, you consider every possible subset of this index set of size Q, right, take this sum, and we require that this sum be strictly less than this sum for all x not equal to 0, right. And if such a condition holds, then this result concludes that by solving the L1 minimization problem, we can actually recover x star, right. So here are a few examples of a matrix A which satisfy a condition like this, okay. For example, if you want to tackle at most 2 adversaries, right, and your x star is of dimension 1, which means that x star is a real number, right, then you can work with a matrix of this form, right. So here one can check that such a condition indeed holds, like for example if k is 1 2, right. So you can see that its cardinality is actually 2. So the left hand side in this case will be x star, because A1 transpose here is just 1 as indicated over here. So x star and cardinality of k is 2, so you will need to add x star 2 times, right, and we require that this be less than, right, the right hand side, which again since all the AIs are the same, right, the left hand side will be 3, sorry, I shouldn't put x star here, rather it should be for x, okay. So we require that 2 times absolute value of x be less than 3 times absolute value of x for all x not equal to 0, right, and since absolute value of x is a positive quantity, right, strictly positive, okay, we can cancel this off, and indeed one can conclude that since 2 is less than 3, this inequality indeed holds when A is chosen in this fashion. One can similarly check for other choices of k, right, and in the same way for q equals 1, and if your x star is of dimension 2, right, such a matrix can handle at most 1 adversary, and again one can check that this matrix A satisfies such a condition for all x not equals 0 and index set k of 1 to n where cardinality of k is 1. So this measurement matrix can handle 1 adversary, this measurement matrix can handle 2 adversaries, and so on and so forth, right. So now this proposition tells us, right, when you had a deterministic system of equations where the measurement is adversarially corrupted in at most q many coordinates, how to recover back x star. So now the question or the goal that we would like to pursue is, can we use this idea, that is the idea that is presented in this proposition 6, okay, to solve this problem. So notice that I have replaced b with expected value of y, right, and I would like to presume that maybe some coordinates of expected value of y are corrupted, right. Can you somehow solve this minimization problem. So of course if expected value of y was known, then you could just use a standard L1 solver, which is actually a linear program. So you could use that and find this x star. However, the interesting case would be when we don't have expected value of y, or we don't know this, instead we have access to samples of this random vector y, right. So that's our goal. And now as I told you, I want to sort of set the stage that motivates the use of 2 time scale stochastic approximation, right. So towards that, let's recall how did we arrive at the stochastic approximation variant of the Marx algorithm. This was the algorithm that we arrived or considered or studied in the previous class, right. So let's first imagine or try to come up with a recipe that helps us identify that the Marx algorithm is one of the potential algorithms, right. So there in the problem setup that we discussed in the previous class, we had no adversaries, right, and hence one can ask, right, in order to solve this Ax equals expected value of y, okay, can we construct an objective function in this fashion, where notice that the norm is with respect to 2, that means this is the L2 or the standard Euclidean norm, right, and we ask, can we somehow minimize this function, right, where we don't have access to expected value of y, instead we have access to samples of this random vector y, right. So one can see that if I write this objective function in this way, and have used this half over here just to simplify our lives, right. So let us say f of x is this function, right, and this one can immediately see equals this expression that we have given over here. This is the sum from I equals 1 to capital N, and this expression is AI transpose x minus the ith coordinate of expected value of y, right. And one can easily see that if I take the derivative of this expression, this will give me an expression like this, right, and you can see that this half helped in cancelling off the 2 that will arise when I take the derivative of this expression, right. So this is the gradient of this objective function. Hence when expected value of y is known, that is this vector is known, right, and you sort of write down the gradient descent, not stochastic gradient descent yet, because we are presuming that we know this vector expected value of y, right. So if you know expected value of y and try to write the gradient descent algorithm, its update rule will be what is given over here, that is we would have xn plus 1 equals xn plus some step size, right, and I want to write the gradient of this objective function with a negative sign, right. So the gradient is over here, I put negative sign over here, and one can see that I would end up with an expression like this, that is xn plus the negative of the gradient times some step size is used to construct xn plus 1. So this will be our gradient descent algorithm, right. Now the problem that we were interested in solving was the case where expected value of y was unknown. Instead what was available to us were these IID samples of y, right, and if you think of the stochastic approximation variant of the Marx algorithm, what we did was wherever this expected value of y appeared, we replaced it with the sample, right, and wherever we had I, we again replaced it with a sample that is chosen in uniformly randomly from the index set, right, and that led us to the stochastic approximation variant of the Marx algorithm. So let me just quickly take you back to that update rule. So you see wherever you had expected value of I replaced it by the sample, and wherever I had I replaced it with this randomly chosen index. So one alternative way of looking at this stochastic approximation variant of the Marx algorithm is to think of it as the stochastic gradient descent algorithm with respect to this objective function over here, right. Now this looks interesting because this in some sense tells us a recipe to construct stochastic approximation algorithms. In particular, it tells us a recipe to construct stochastic gradient descent algorithms, right. So one can ask, okay, this works well when there are no adversaries and we are working with the L2 norm in the objective function. recall that in the presence of adversaries we would like to work with the L1 norm of this objective function, right, and one can ask, can I construct the stochastic gradient descent version, the stochastic gradient descent to minimize that algorithm, that objective function itself. So that is what I have written here. So the question that one can ask is, can we follow a similar recipe to what we followed in the previous couple of slides, right, and derive a stochastic approximation, or more specifically a stochastic gradient descent algorithm for minimizing the this objective function, where notice that here we have 1 instead of 2, right. So as we did in the previous slide, this objective function can be expanded in this fashion. That is, we can write this objective function as the sum going from I equals 1 to capital N, and you have the absolute value over here. Notice that unlike the case where we had the L2 norm, here there is no square, right. So that is the difference between an L1 norm and L2 norm, right. So again one can ask, okay, let us first look at the gradient descent of the algorithm presuming knowledge of expected value of y, right, and then what we will do is, in order to derive a stochastic gradient descent, wherever expected value of y appears, maybe we will just try to replace it with its samples, right. So that could be one approach to do. So towards that, if you try to look at the gradient of this function, we will end up with something like this, because you have an absolute value over here. Of course this function is not differentiable, the absolute value function is not differentiable where the argument is 0. So except for that scenario, that is when the argument is not 0, this function is differentiable, and the value of the derivative is either +1 or -1 depending on whether the argument is positive or negative, right. So with that concept in place, one can see that the derivative of this expression equals this, right, for all x such that AI transpose x not equal to expected value of y of I, right. So let us try to work with such a scenario, and then we will worry about what to do when AI transpose x equals expected value of y. So let us presume that for every x where these arguments are not 0, right, this gradient is well defined, and let us see if we can use this expression for the gradient to come up first with a gradient descent algorithm and then with a stochastic gradient descent algorithm, right. So with regards to coming up with a gradient descent algorithm, let us first presume that we have knowledge of this expected value of y vector, right. So if this vector is known, right, then the gradient descent algorithm is given over here, which is basically xn plus 1 equals xn plus some step size times the negative of this gradient, right. So since we want the negative, what I have done is, whatever is this expression, notice that I have flipped it, right, that is I have taken this expression multiplied with -1 to get this expression, right, and this then can be viewed as a gradient descent algorithm for minimizing this objective function, right. So with this update rule in place, one can ask, can I come up with a stochastic gradient descent version of this algorithm to tackle the case where we do not know expected value of y, instead we have access to samples of this vector y, right. So the naive approach to come up with a stochastic gradient descent algorithm is given over here, right. So this algorithm has the update rule xn plus 1 equals xn plus something, but observe that here instead of putting in expected value of y or some appropriate coordinate of expected value of y, I have replaced it with the sample of that vector, right. So one can say, okay, this looks like a nice algorithm, can I work with this algorithm as in the Cox-Marx algorithm case, that is in the L2 case we just took the gradient descent algorithm, wherever expected value of y was there we replaced it with a sample, right, and using your standard stochastic approximation theory, one can show that that algorithm converges to the desired place. So one can ask, in the L1 norm case as well, would such an algorithm behave or help us estimate the desired quantity, which is, or minimize the L1 norm of Ax minus expected value of y, right. Unfortunately that is not going to happen, and the reason for that is if you define Fn in this fashion, that is the information that we have at time n, then in the L2 case, whatever your update was, if you take its conditional expectation with respect to the information that you have at time n, then this expression equals this, and this quantity over here matches the true gradient at x, right. So this quantity over here matches the true gradient at xn, sorry I said x, I should have said xn, right. So this quantity matches grad f of xn, where your f is defined using the L2 norm. Is this okay? So one can show that this matches. I mean, we may have to play with these constants a little bit, but other than the constant, okay, the expression for grad f of xn is given by this expression over here, right. And because of this reason, one can think of as the Cox-Marx algorithm as trying to do a noisy gradient descent. That is exactly what is stochastic gradient descent, but the conditional expectation of the update is aligned with the true gradient. That is what in some sense makes your algorithm work, because our stochastic approximation theory somehow ensures that the cumulative effect of the noise is asymptotically cancelled out, and hence the update direction is eventually directed along the true gradient, negative of the true gradient direction. That is why in some sense one can say that the stochastic approximation variant of the Cox-Marx algorithm works. However, in the L1 case, if you take the conditional expectation as we did here, okay, this will not equal the gradient of your L1 objective function at xn. The reason being that the sine function is not a linear operator, and because it is not a linear operator, expected value of sine is not equal to sine of expectation. That is, you can't interchange expectation of sine. If we could do that, then of course we would end up something like this, because notice that this expectation, if it were allowed to go inside, then the expectation of this quantity will be expected value of y of I, where in plus 1 is sampled uniformly randomly. So maybe I should add 1 over n here, right. So this will be 1 over n, right. So unfortunately this conditional expectation will not equal this, and which implies that, right, this algorithm that we have over here, this naive algorithm, in an asymptotic sense is not behaving like the gradient descent algorithm, right. If we had such a thing, then indeed this algorithm's behavior would be at least in an asymptotic sense mimic that of your stochastic gradient descent sorry, not stochastic, rather the gradient descent algorithm with respect to the L1 objective. However, since this conditional expectation does not equal this, right, even asymptotically this expression will not mimic the behavior of your gradient descent algorithm with respect to the L1 objective. So this is the reason why this naive algorithm, right, is not principally constructed, right. So how do we handle this? And that is where we come up with 2-time scale stochastic approximation algorithm. Okay, so the idea simply is that we estimate expected value of y separately and use the estimate, okay, in xn's update. Basically what you do is you write down the same update for xn, except that wherever you had calligraphic yn plus 1, right, which was like one sample of y of in, right. So y of in, one sample of that. So instead of writing capital Y of in or calligraphic yn, which is basically a sample of this, what I now do is I have little yn, and here I have maybe I should be careful, I should have placed in plus 1 here. Let me write this properly. Okay, so this is in plus 1, right. So yn plus 1 was basically a sample of this thing, and in my previous algorithm I had directly placed this quantity over here, but here instead what I am doing is, instead of plugging in calligraphic yn plus 1, I am plugging in the in plus 1th coordinate of little yn, where this little yn is updated separately, right. In particular, this quantity tries to estimate expected value of y. In particular, I should be careful here, so there are some typos. This is just yn, sorry, this was correct. Okay, so I should say for all I you update your yn of I in this fashion, right. So what is happening over here is that your yn, okay, is a vector whose dimension equals the dimension of your expected value of y, and you update the ith coordinate of yn in this fashion, right. So we are updating it in this fashion, and in order to construct this, I am at this point presuming that there are no adversaries. I will first come up with a stochastic gradient descent type algorithm for minimizing the L1 objective, and then in the next class we will see how to handle adversaries. Okay. So here this little yn in some sense is trying to estimate expected value of y. I will soon tell you why it estimates that, right, and whatever is the ynth estimate at time instance n, I will look at the in plus 1th coordinate of that and use it here. Is this okay? So if you remember, if I had calligraphic yn and I took the conditional expectation of this expression, right, the expectation and this sign couldn't be interchanged, right, and that sort of prohibited me from concluding that you are somehow making use of an estimate of expected value of y over here. In contrast, observe that here, since I have replaced this calligraphic yn with little yn, right, and if I am doing this algorithm appropriately, one can hope that this yn actually converges to expected value of y, right, and this part will ensure that at least as n goes to infinity, here I am actually working with expected value of y, and since I am asymptotically working with expected value of y, this algorithm, that is the xn update, can be presumed at least in an asymptotic sense, okay, mimicking the behavior of a stochastic gradient descent algorithm with respect to your L1 norm. Okay. Now let me quickly tell you why this algorithm is like the one of the natural ways to estimate expected value of y, right. So again let us look at the conditional expectation of this update rule, right, and since we have presumed that your in plus 1 is sampled uniformly randomly, so in plus 1 will equal I with probability 1 over n, right, and this is an indicator that at time instance n in plus 1 equaled I, right. So if you take the conditional expectation of this with respect to the information that you have at time instance n, one can see that the conditional expectation will actually be summation I equals 1 to n, right, and n times, okay. Now your in plus 1 could be one of the many indices, right, and since we are focusing on, so maybe I will write it as j equals 1 to n. So one can say that this expression is actually expected value of y of j, and the probability that in plus 1 equals I is basically 1 over n, and hence this expression will actually be times 1 over n, right, and this n and this n will cancel off. Let me just make sure I am doing it correctly. Sorry, let me do this properly. Okay, so for a fixed I, this expectation will basically equal n times expected value of y of I times 1 over n, right. One can check that the conditional expectation of this with respect to the information that you have at time n, and using all your independence properties, one can show that the conditional expectation of this expression is actually this, right, which would imply that these n's cancel off and we have expected value of y of I over here, right, and in this sense this update rule can be rewritten as yn plus 1 I equals yn of I plus beta n times expected value of y of I minus yn of I plus some noise sequence. Is this okay? And this expression, right, if you had just this expression, one can see that this quantity in that spirit tries to compute expected value of y, expect the ith coordinate of expected value of y. In particular, if you sort of apply your the stochastic approximation analysis, in particular the ODE method that we have studied so far, for this update rule, one can see that this update rule indeed tries to estimate expected value of y of I, right. So in other words, the ith coordinate of yn tries to estimate the ith coordinate of expected value of y in an asymptotic sense, right, and by making use of this quantity within the sine function, we are ensuring that as n becomes larger and larger, we are indeed working with an estimate of the true gradient. Okay, that is what ensures that this update rule in an asymptotic sense behaves like a stochastic gradient descent with respect to the L1 norm, right. So what one can do is we can take these two update rules for xn and yn and rewrite it in this fashion, right. This is some exercise that you can do, where one can see that h of x comma y has an expression like this, and the expression of g of x comma y has an expression like this, and your noise terms have expressions like this. Is this okay? So this is something one can check, right, and you can see that now your xn plus 1 and yns, right, they are updated using two different step size sequences, right, and because you have two different step size sequences, one can conclude that this algorithm that we have has a 2 time scale nature. In particular, whenever your alpha n's and beta n's are updated using two different step size sequences, we will say that we have a 2 time scale algorithm. Okay, so this brings me to the end of this class, right. Let me quickly summarize what we have done in today's class, right. We looked at minimizing the L1 norm of Ax minus expected value of y, right, and we saw that if you try to come up with a naive gradient descent algorithm or a naive stochastic gradient descent algorithm, right, the expectation and the sine function do not interplay with each other, in that the expectation and sine, okay, cannot be interchanged, and because it cannot be interchanged, right, this stochastic algorithm does not behave like the stochastic gradient descent of your like the stochastic gradient descent for minimizing the L1 norm, right. So to counter this issue, what we do is we estimate these expected value of y separately, right, and whatever is that estimate we directly plug in into the sine expression, right, and by ensuring that this alpha n and beta n are step sizes of different orders, we end up with a 2 time scale algorithm, right. In the next class we will see what role do these step sizes play, and how can such an algorithm be analyzed. I would also like to highlight that in the later half of today's discussion we sort of did not consider adversaries, right, that was just to keep things simple. In the next class we will ask what if we had adversaries, and how will this algorithm tackle the adversarial measurements and so on and so forth. Okay, so that in some sense will be taken care of by what is known as stochastic recursive inclusions, and that will be discussed in subsequent classes. Until then, goodbye, thank you and namaste.